Yeah, so the slides of Professor Abramovich's talk is already uploaded on the website. So if you want to download it, you please go to the website. Yeah. So are you ready? Okay. So welcome back to the afternoon session. So we're happy to have Professor Dan Abramovich to give a second lecture, which is a resolution of singularities for everyone. Please.
Thank you very much. Can you hear me, please? Okay, thank you. Okay, so I very much hope this will be for everyone in this audience. And I would like to start with a little bit about blowing up, because the way you write blowing up, the particular way you choose to write blowing up may help seeing how singularities behave under blowing up. So we all learned, this is a birational geometry conference, we all learned how to blow up. So here's an example. Say we want to blow up the XYZ space at the origin. And we learned that there are 3 charts, one for each of the variables defining the locus we blow up. For instance, in the X chart, X is the exceptional variable, and we have to transform Y and Z. So Y prime and Z prime are the new transformed variables. XY prime is Y, and XZ prime is Z. So you pull out the exceptional of any of the original variables. And then for the second chart, you do something similar. And one thing we often struggle with is how to go from one chart to the other. So it's maybe not as pleasant as we would wish, but we all learn how to do it. And it's very useful to learn how to do it. But you can still ask if there's a better way to do it, where you can immediately see how things work without worrying about charts and transformations. And this has been known for a while. So this is what is known as the Cox construction nowadays, except that it has been discovered in one way or another several times over the history. And I find it very useful, at least when proving that how things behave under blowups for the purpose of resolution of singularities. So let's do the simplest possible case. Y is the affine space with variables x1 through xn. And I want to blow up the ideal generated by the first k variables. So if you wish, the locus I'm blowing up is the locus whose equations are these. So the parameters along the locus, for some reason I called it x here. X becomes something else later on. The parameters along the locus are xk plus 1, xk plus 2, etc. But the defining equations are x1 through xk. So the way you blow up using the Cox construction, you first define a variety which I'm using Wodachik's notation. B stands for Bordism or cobordism. B is a variety where you add several variables and you mode out by equation. So S is an exceptional variable. X1 prime through xk prime are the transforms of these variables. With the equations as before, xi equals exceptional times xi prime times the transformed variable. So the rule is the same, except that there's only one chart and only one exceptional variable for now. So I find it quite convenient. So how do you get to the blow up from this variety B? You still need to do a couple of operations. First of all, you remove the locus where all the transformed variables vanish simultaneously. That's the analog of requiring certain variables to be units. In the standard notation. We have a C star action on this variety, both on B, and it fixes this locus, so on B plus. The C star action acts with weight 1 on the xi, on the transformed variables xi prime. It acts with weight -1 on the exceptional variable. And the reason we do it is so that the product, which is the original variable, is invariant, the C star action doesn't see it. So there's a C star action acting trivially on the original Y, but acting in an interesting way on B and on B plus. And the blow up is simply the quotient of B plus by C star. So if you are comfortable with C star actions, I prefer to present the blow up in this way rather than the usual charts. Okay, and hopefully I'll show you that this makes some proofs of in the context of resolution singularities transparent. But before I do that, let me show you that this is really nothing new. This is something familiar. So let's go back to charts. Let's see how the original charts are manifested from this description. So I repeated here what B is and what B plus is, and what the blow up is. If I want to go to charts, I want to declare one of the transformed variable. I want to take a slice of the C star action. I want to declare one of the transformed variable to be 1. So let's say I declare xi prime to be 1. That is a slice of the action, so that I no longer have a C star action once the locus where xi prime is non-zero is spanned by C star orbits with exactly one point on which xi prime equals 1 on each orbit. So that's what I mean by a slice. On this slice, if xi prime equals 1, then what does this equation say? The equation say that s times xi prime, s times 1 equals xi. So s equals xi. So on this slice, I might as well replace xi by s by xi, so I get the original charts that we learned, for instance, in Hartshorne or in any class we took about Birational geometry. So it's the same thing, but it has the advantage of having one chart. It also has the advantage that we don't need to worry about projectivizing, etc. Questions? The next thing I want to tell you is what this P is. So I came to believe that in some sense B is more fundamental than the blow-up itself. It's something that is also familiar to you if you have, for instance, read Fulton's book about intersection theory. B is the deformation to the normal bundle. So B has variable s and the extra xi prime. Because there's a variable s, it maps to spec C of s. So it maps to A1, right? So let me draw pictures. So here's I'm drawing here x, and here's y. This lies over s equals 1. So oops. Don't worry about that. So when I set up s equals 1, I think I was here. When I set s equals 1 in all this equation, then xi become equal to xi prime. So I might as well throw away S because I set it to 1, and I throw away xi prime because I said they are equal to xi. So the fiber of B over 1 is just y itself. When I set S equals 0, then this equation forces all the xi to be 0, and the xi prime vary freely. So I get an affine space corresponding to the xi prime. So for each point in X, I get a whole affine space. So what do I get? Where is my picture? So maybe I'll draw it in a different color. So the fiber with S equals 0, this is the normal bundle of X inside Y, the total space of the normal bundle. So what you get here is the deformation to the normal bundle. The C star action, I should draw a picture of the C star action, but first maybe I'll fill up the family of copies of X. So there's a whole family of copies of X over the whole affine line. It's only Y, the ambient space, that is degenerating, and the orbits of the C star action look like this. Along the 0 section, the orbits go when S goes to 0, when T goes to 0, when T goes to infinity, the orbits lead to S equals 0. Here, orbits expand. So this is the way the action goes. Remember that we are going to remove the locus where xi prime is 0. The locus where xi prime equals 0 is precisely the family, the constant family of X over an affine line. Right. So on the one hand, you can recover the deformation to the normal bundle from the blow-up, as you see in Fulton's book. On the other hand, in some sense, the deformation to the normal bundle is more fundamental than the blow-up. You can recover the blow-up through the Cox construction from the deformation to the normal bundle. And as we'll see later, it enables us to make computations in an efficient way. Yes, there's a question there.
Blow up the copy of your center. So I'm using.
No, I gave you a procedure that doesn't say the word blow up at all. It's spec of something. Spec is more fundamental than proj, right? So, and you can write explicitly spec of what algebra it is. It's so the maybe I might as well use my space for notes. So what is B? What is B? Say again? But it's not because it's different from the part. But so what is B is a spec over Y of the direct sum, but it's not a proj because I'm taking from minus infinity to infinity of how shall I in, where in is I to the n, where n is bigger or equal to 0, and O and n less than or equal to 0. So it's a very simple algebra that you make out of the ideal that you want to blow up. Of course, it's related. I'm not, I'm not saying that you should not learn about proj. Okay. But hopefully I'll convince you later that this is quite useful. Incidentally, I think there are microphones if people want to be heard in the Yeah, okay. From the Cox construction to charts. Okay, and I told you what B is. Oh, yes. Okay. Okay, so that's about B. Now I want to change gear. I want to tell you about resolution of singularities from my point of view. And as you may have heard, my point of view uses stacks and uses weighted blowups, but weighted blowups in a stack theoretic sense. And you might be a little afraid of it, but the next slide will show you that weighted blowups are as easy as usual blowups. You just put little WI somewhere. Okay, so let's do that. So let's do the Cox construction for weighted blowups. This is again something that was discovered several times over history. The particular presentation is basically due to Quek and Reed. There's a paper about weighted blowups that has been in the writing for at least 3 years. It's basically complete, and you can find it on David Reed's webpage, but it's not yet on the archive. David Reed is very careful about only giving the final product at the end. But you can find it on David Reed's webpage. So the weighted blowups, so the notation I use for the weighted blowup, where I give x1 weight w1, xk weight wk, is this notation. So I'm thinking of, basically I'm thinking of putting things of weight 1 in each slot. So since x1 has weight 1, x1 to the power 1 over w1 has, sorry, since x1 has weight w1, x1 to the power 1 over w1 has weight 1. Okay, so maybe I should, oh, sorry. Oops, I should do something permanent. The weight of this is 1. So the weight of everything I write here is 1. Right, so let's blow up this gadget, and I guess in this crowd, I'm allowed to say the word Q ideal. So this is not an ideal I'm blowing up, it's something more complicated. It's represented by Riesz algebra or a filtration of ideals, but you can think of it as a Q ideal. A model of this weighted blowup is writing B that is now dependent on the weights that I chose. S is again the exceptional variable, xi prime are the transformed variable, and the only change is that the equation relating xi and the new variables has s to the power wi in the. You are not happy. Somebody is, yeah. Okay. Is what equal to what? K equal to D, yes, absolutely. You have a reason not to be happy. It appears twice already. But you know, in a minute it will disappear because okay, so this is B. It has again a C star action, and now the C star action, I want to make the C star action again so that the product will have weight 0. So multiplied by e to the 0 by 1. So the weight of S is -1. The weight of xi prime is sorry, xi prime lies is acted by weight wi. Xi prime has weight wi, and S has weight -1. So the exceptional always has weight -1 in the Quek and Reed terminology. Okay. I create B plus with the same rule. I just remove the locus where all the transformed variables vanish simultaneously. I take the quotient and the quotient. So now the big difference is now the C star action is not free. So in order to work things out so that the result is something smooth rather than with quotient singularities, I insist on working with this associated quotient stack. And this is what I call the blow-up, the weighted blow-up along this weighted center J of Y. And once again, B is itself a more fundamental object. It is the degeneration to the weighted normal bundle or weighted normal cone, whichever way you want to call it. The only, I mean, there are questions you can ask. What is the weighted normal bundle? I can discuss that later, but it's less critical for understanding equations and how they transform. So questions about this? I will give you in a minute a description in terms of charts. And I think you'll agree that the description in terms of a C star action is going to be easier than the description in terms of stacks, of charts. Okay. Right. So so there will be a lecture of Wodachik later this week, and he prefers, instead of working with this, with the quotient stack, he prefers to just keep the variety B plus with the action of C star. So at the end of his procedure, he will have a variety of higher dimension with a torus action, and the quotient is going to be, the quotient stack is going to be the resulting blow-up. So I prefer to think about stack quotients, but the approaches are equivalent. Let's look at charts. And in a few minutes, we'll also have some examples, but okay. So I just copied the definition. Let's take the slice where xi prime equals 1. This time, xi prime equals 1 does not kill the entire C star action. There's still a remaining subgroup that fixes the locus xi equals 1, which is the group of roots of unity of order wi. Since the action on xi is by t to the power wi, roots of unity act trivially. So this is the way that group of roots of unity acts. And if you plug in xi prime equals 1 with this action, you have this stack theoretic presentation of the quotient. So instead of getting rid of S entirely, S becomes the with root of the original variable in this chart, and the other equations remain the same. And then you have to mod out by the action of the residual group. And of course, there's a way of transforming from one chart to the other, but I prefer to work with Genia's neighbors formalism, the Cox construction, and work with one chart with a C star action, and everything is described by that one chart. Okay, so that's about blowups.
The exception is the weighted projectors.
Right. So remind you a name. What? Oh yes, you are. Of course, you have a different. What is the exceptional? So wait, which? Yeah, let's have it here. The exceptional is the locus where is defined by S. S is the exceptional variable. So if you set S equals 0 here, what these equations say is you get rid of xi, and but you have new variables xi prime with s is 0. So and you have this action. So you take affine space modulo this action. So for each point on X, on the locus you are blowing up, you have affine space minus the origin, because you removed the locus, modulo this action. So it's precisely a weighted projective space, except that I like to work with a stack theoretic weighted projective space. Okay. I accept everyone. If you want to work with a scheme, okay. Are we ready to talk about resolution? Okay. What is a resolution of singularities? It's a proper birational morphism from something x prime to x, so that x prime is smooth. And again, I will allow x prime to be a Deligne-Mumford stack. It will be, I'm satisfied by resolving by a Deligne-Mumford stack. Again, Wodachik instead allows x prime to be a higher dimensional smooth variety with an action of a torus with finite stabilizers, so that the quotient is proper and birational. So that's his version of, instead of working with a stack quotient, he works with a higher dimensional variety with basically a global quotient situation. These two approaches are almost equivalent. Again? Well, he explicitly wires into his processes that it's always a global quotient. So I deduce at the end, I mean, okay, so. We work together, so we like to argue. It's more fun to argue when you work together. Even so, I like to work with algebraic stacks, but even so, there are aspects of algebraic geometry that are not as well developed for stacks as for schemes. And maybe you want to go back to a scheme at the end. So hopefully we might have a chance to discuss. At the end of the process, I will have a smooth stack, or Wodachik will have a higher dimensional variety with a group action, such that the quotient is has quotient singularities. At the end, you may want to have a smooth variety, and the process for doing that is either I put it under the general name distackification. So you take a smooth stack, you do some stack theoretic operations so that the coarse moduli space becomes a smooth variety. This is I will just say what the process is about. I will not give you a complete description of it, but it's a well-known process. It's combinatorial. It's not so hard to understand. And I had undergraduates code it in a new system called Oscar. So it can be done. I don't insist, but I get abelian quotient singularity. So I might as well say that that's what I get. Okay, so let's see how to resolve various kinds of varieties. And we start from curves, as usual. So consider a singular curve. And let's take a singular point on the curve. What do? You blow it up. You just do the usual blow up for now. And you read in Hartshorne that the arithmetic genus of the blow up is smaller than the arithmetic genus of the curve. So because of that, at some point, you cannot, the arithmetic genus of a curve cannot go, for instance, if it's irreducible, it has to be non-negative. So at some point, this must stop. And therefore, the reason it stops is that it's no longer singular. You cannot do it again. There is an advantage of working with weighted blow-ups. The efficiency of the process can be made higher with weighted blow-ups, but I'll put it aside for now. This is not critical. Let's look at surfaces. And my favorite example is the Whitney umbrella. So whenever you have a chance to draw the Whitney umbrella, do it. Familiar? So this is the Whitney umbrella, and of course it has double points all along this line, but clearly the pinch point is the more singular point. Okay? The x coordinate goes in, the y coordinate is the horizontal coordinate you see, and which measures how thick the slice parabola is, and the z coordinate is the handle of the umbrella. So there was a typhoon this last few days, and Whitney would get very wet in the typhoon. So let's see what happens when we try to mimic what we do for curves. We blow up the worst singular point and immediately go to the z chart because that's the most interesting chart. So what happens in the z chart? In the z chart, I write my transformed variables are x prime and y prime, and x is z times x prime, y is z times y prime. So I plug in x prime z for x, y prime z for y. I get this equation, and I reorganized it this way. That's a little exercise that we all did when we were beginning birational geometers. And what do we see? We see this is the exceptional part that we can pull out. And this is the proper transform, which looks exactly, and so the z square factor is exceptional, and the other factor exactly as we started. Okay, I use charts here, but I urge you to see what happens when we do the Cox construction. Of course, it won't help. We haven't improved the singularities by just doing this. The Cox construction will just look a little different. It will emphasize that the z you see here is really the exceptional variable and not the original. This becomes exceptional. Okay. And I put exercises through the notes, and if we have time at the end, we can go through some of the exercises, whichever ones you ask me to do. So of course, we know how to resolve singularities of surfaces. So classical approaches have ways to go around this problem, but I don't want to discuss it. I want to discuss the method using weighted blowups, which is still based on Hironaka's approach, but with the addition of weighted blowups. So consider the same equation, but now I want to blow up something that keeps track of which degree each variable appears in. Remember, however, this is not the way I wrote the center for weighted blowup. I wrote it with weights with powers that are 1 over weights, right? So in order to do this, I have to rescale the powers by 1 over 6. So I get the powers are all 1 over an integer. Okay, so this is take this center and raise it to the power 1/6. You get this center. I haven't told you what a center is really, but I said it's a Q ideal. But you can imagine that that's the right thing to do. So let's do this. So I think I'm supposed to write this out explicitly here. So again, x squared plus y squared z equals 0. Is that the equation I started with? Yeah. Oh, minus y squared z. Oops. And I'm plugging in. Now what I need to plug in is x equals, I'm blowing up x to the 1 cubed, y to the 1/2, z to the 1/2. So this means I need to write x equals s cubed x prime, y equals s squared y prime, and z equals s squared z prime. Plugging it in, I get, okay, so s to the 6. So I know that s to the 6 will pull out. Okay, so again, this is exceptional. And this is the transform equation. And I claim that something got better. It looks the same, but don't forget, I'm removing the vanishing locus of x prime, y prime, z prime. So I no longer have the worst singular locus in this picture. So the equation became, the singularities became better. So again, the S6 factor is exceptional. The other factor is exactly as we started, but we removed the offending locus. And now exercises that we can revisit later on. Yeah, I think we should have a chance to do some of the exercises. First of all, in characteristic 0, show that this is in fact an improvement, that the only remaining singularities are double points or normal crossing double points. Another exercise to complete the resolution, blow up whatever remains to be blown up. And another exercise is to repeat the process for Yaroslav Odachik's favorite example, x squared equals y1, y2, y3. You can always stop me if you want to see something worked out, but this is something that I urge you to do on your own, and maybe we'll do together later on. Okay. Now, is this still a resolution of singularities for everyone? Have I lost somebody? Oh, this is that. I don't know how to ask this question so that I actually get responses. Okay, which page am I on? 13. Yes. All right, so that was about resolution and about what happened in a couple of examples. So we know what resolution is. We saw that resolution of curves is sort of works like in an ideal world. Surfaces are not so ideal if you work with usual blowups, but suddenly with weighted blowups, something worked very nicely. Yes, Hamid. Well, in this case, of course, I chose something to make it homogeneous. So I know that x appears in degree 2 and y and z appear in degree 3, and that's how I chose the weights. I will show you in a bit how you, towards the end of today's lecture, I'll show you how to choose the center, how to choose the invariant of the singularity, which involves the 2, 3, and 3 here, and how to choose the center. So you would miss something. If you chose 1, 1, 1, or 2, 2, 2 is the, if you chose 2, 2, 2, you would get the standard blow up, which will not get you any better. 2, 1, 2, yeah, I mean, okay, I think Hamid insists on doing the example with 2, 1, 2, and I claim it will not work. Yeah. So you want 2, 1, 2. So S, so S x prime equals x, s squared y prime equals y, and s z prime equals z. So right, if you have x 2y z2, and you want to rescale it, you have to rescale it by 1/2, and you get x to 1/2. No, x to the 1. Y to the 1/2, z to the 1. So that's why I have the power 1 here, 2 here, and 1 here. Okay, so let's just plug in and see what happens. So I plug in sx prime for x, I get sx prime squared minus s squared y prime squared times sz prime equals 0. I can pull out s squared here, and I can pull out more than s squared here, but okay, so the only s squared comes out. And I think I have s to the 3rd y prime squared z prime. What's that? X prime squared, you're right. So if s is a unit, I get right. So, and I'm removing the vanishing locus of x prime, y prime, z prime. So, okay, so when z prime is non-zero, you get an equation, let's call it u. So you wanted not this one, but okay, so you want x, y squared, z. Okay, we can spend the rest of the day doing this. Okay, so if you do that, then instead I have s to the 4x squared minus s x prime squared my s y prime s squared y prime squared and s squared z prime equals 0. So you can pull out s to the 4. Yeah. Oh, okay. So you chose it. You chose another supporting hyperplane of the Newton polygon. So this also works. It's s to the 4 times x prime squared. So this is an example where you have more than one supporting hyperplane of the Newton polygon, and it shows that you have more than one choice. But I'm giving you one canonical choice, and that will, okay. You're absolutely right. There's more than, and in characteristic P, you have to search for another choice, it turns out. We may have a chance to talk about it. So this is actually a very good point.
But after your lectures, we'll know how to choose the weight.
What's that?
After your lectures, we'll know how to choose the weight.
I think before the end of this first lecture, you'll know how. If I don't do too many examples, yeah, you'll know how to choose the weights. Yes, that's what I hope to gain here. Okay, so I'm going back to Hironaka and people following Hironaka. So there's a process by which you reduce the resolution of singularity to something else. This is called principalization. Or principalization is a process to which you reduce resolution of singularities. So a principalization is something you do to an ideal on a smooth variety. So say you have an ideal shift I on a smooth variety Y. Principalization is a proper birational morphism such that the ideal you get is exceptional and locally principal. This is a very weak requirement. Okay, so if later on we'll insist that Y prime will be smooth. So if we don't insist that Y prime is smooth, we can just blow up the ideal I. The blowing up of the ideal I does this. But then we didn't gain much because we made a smooth variety singular. So maybe I forgot to write, so I want Y prime smooth, except that this will disappear in a minute. A principalization is logarithmic if the vanishing locus of the new ideal on I prime is a simple normal crossing divisor, which presupposes that Y prime is smooth. So Y prime becomes smooth, and the ideal is a simple normal crossing divisor. So at any y, the ideal becomes a monomial in local parameters. Okay, so that's when a principalization logarithmic. I will not, for today's lecture, I will not insist on this. I will want something, so we'll be interested in a strong principalization, which takes a smooth variety and gives you something smooth, obtained by successively blowing up or using either classical or weighted blowups of smooth loci inside the vanishing locus of I. So you want to always blow up inside the vanishing locus and always blow up smooth things. And one further exercise. So this exercise is basically saying, suppose that you have a smooth variety, subvariety of a smooth variety, and you take its ideal. How do you principalize that? Well, you can just blow up the ideal of the variety. Since the center is smooth, you can blow it up. If the variety is a divisor, that blow up is actually a trivial birational operation, except that it comes with a declaration. This locus is now exceptional. A divisor becomes exceptional by blowing up the divisor itself.
There, I think there's a question from chat.
Okay. Logarithmic. It's called logarithmic because the result is what you get with a logarithmically smooth variety. So a variety with a normal. So logarithmically smooth is a synonym in birational geometry for a smooth variety with a normal crossings divisor. I hope this answers the question. I mean, oh, yeah. You're welcome. Okay. Right. So I will, at least for this lecture, I will not do logarithmic. I will do strong. And why do I want strong? So there's a little piece of magic in resolution of singularities, which is that strong principalization implies resolution, at least if you can embed your variety. So we claim that strong principalization can be used to get resolution. And the assumption is that you can embed your irreducible variety, very singular variety X, in a smooth variety Y. What you do, if you can't embed, you locally embed and you make sure that you can do it globally. Okay, so consider the ideal of the subvariety X as the ideal you want to principalize. And let's see what happens in the principalization process. A strong principalization will make the ideal principal and exceptional. But being strong means that every time you only blow up smooth loci. Now, you make everything exceptional, means that the generic point of your original variety has to be blown up because it has to become exceptional. So it has to blow up the generic point of the proper transform X prime of X at some point. But it's a strong resolution. I'm only allowed to blow up smooth things. So at the point that that the principalization achieves this blow up, at that point, X prime has to be smooth. So, which means that principalization, strong principalization, if you can achieve strong principalization, you can achieve resolution, at least if your variety is embedded. In order to, in general, we only have local embedding. And as hopefully I'll explain this. This is the fact that we have only local embedding is addressed by embedding things locally, resolving them locally, and making sure that the process of resolution, process of principalization that you use has some factoriality properties that guarantee that things will glue together. So there's the first is smooth factorial, or factoriality under smooth morphisms. And the other principle is the re-embedding principle that I will discuss in a little bit. Oh, actually, I will discuss immediately. So smooth factoriality demands that if I have a smooth morphism from one variety to another, then the principalization of an ideal here is the, when you pull it back, it gives you the principalization of the ideal here. So principalization of an ideal on Y is the same process as principalization of the ideal on Y prime. If you want to be formal, functorial, smoothly functorial principalization is a functor from pairs of an idea, variety with an ideal, with arrows given by smooth morphisms to principalizations. But let's not be too formal. So that's about smooth factoriality. What is the re-embedding principle? Re-embedding principle says that if you have a if you take your variety and take a product with A1, and you do what somebody told me a while ago, you blow up the original variety on the fiber at 0. So to take the I plus the plus Z, so the principalization of this ideal has the same series of centers as principalization of the original ideal in the fiber at 0. So there's it's a compatibility between. What I meant to do is draw a picture. So here's. So you have an ideal. This is the ideal that you want to principalize on this variety Y. The sequence of blowups that you'll apply here is the same as the sequence of blowups that you'll apply when you try to principalize the ideal of the same subvariety but embedded in Y cross A1. So that's the re-embedding principle. Is a requirement on a principalization process that will ensure that we can deduce from it resolution. Okay, questions about that? Is there a question here? No. Okay, so now we know that we need to produce for ourselves a strong principalization procedure that satisfies smooth factoriality and the re-embedding principle.
How will we use the re-embedding principle? What is it used for?
It's used so you can, I mean, sometimes you embed one patch of your variety in a variety of dimension k, and another patch in a variety of dimension k plus 1. The intersection will have two embeddings, one in dimension k and one dimension k plus 1. They differ, so you use a tau equivalence to show that this means that you basically have an embedding in a variety Y cross something smooth, and you might as well make the something smooth A1 by a tau equivalence. So we'll get there. Hopefully I'll say something about how we deduce this, but this is among the things that we should write to ourselves as. So anything that is red here is something that you may want to ask me to show you tomorrow. So tomorrow I'll go through proving various things, and I don't know that I will cover everything, but there are things that you may want to ask me. Is this fair? Okay. Okay, so both, this is what I'm saying here. Both are automatic in our resolution algorithm, and both are anyway desirable, and we'll prove them. So now we'll do some derivatives. We did some. We'll also do some algebra, but a little bit of calculus is never bad. How am I doing with time? Okay, I think I'm okay. Suppose I have an ideal, Y, just for simplicity, Y is affine space. It doesn't, I mean, the same ideas work in general. So define the derivative of the ideal to be what you get when you throw into the ideal also the derivatives, all the derivatives of all elements of that ideal with respect to all variables. Okay? And we'll have a couple of examples in a bit. For today's discussion, I'll define dn of I to be the iterated process of taking derivative n times. Here's an exercise, compute d of I and d square of I when, let's do one of these. So I equals x squared plus y squared z. D of I. So, okay, so I need to use the elements of the original ideal. Here I have just one generator. I need to take the x derivative. I need to take the y derivative, and I need to take the z derivative. Okay, so this is it. You can simplify, but it's not. So because I have, because I have these elements, I don't actually need the original elements of the ideal. This is a general phenomenon. If I want to calculate d squared of I, well, one thing I notice is that if I take the x derivative of this, I get 1. So I don't need to worry about other derivative.
Characteristic 0.
And characteristic 0, yes. Did I say that I'm working in characteristic 0? I'm working in characteristic 0. I'm not going to give you a resolution characteristic P today, or not in the near future. Okay. So we did at least one example. This is an example that may take more time, and one needs to sit at home and do it, or in the hotel room. I'll explain the star here. The star is what is the right notion in positive characteristic. Some of you know the answer, and some others may want to learn, but it's not necessary for this lecture. So doing iterated derivatives is not the right notion in characteristic P. And doing things in mixed characteristic is an entirely different beast. I'm not going to even guess what you want to do. Here's an important exercise. If you have a smooth morphism and you pull back the ideal, then the derivative of the pullback ideal is the pullback of the derivative ideal. Okay? And for this calculation, you might as well assume that a smooth morphism is, again, a product with affine space. That's an illuminative enough example. If we get to it, we can do the exercise later on. Let's calculate the order of an ideal at a point. So the order of the ideal at a point is the first time that I get the unit ideal at the point. And you define the maximal order of an ideal to be the maximum of the order of the ideal of all points, at all points. And let's do one example. So convince us, first of all, So the first exercise to convince yourself that ORD is upper semi-continuous. I'll give you a hint in a minute. Also convince yourself that the locus where the maximal order is attained is closed. That's related. And compute the maximal order in the 3 examples. Okay, so we can do it in the example here, because we calculated I. We calculate D of I. D of I is not a unit ideal. We calculate D square of I. That is the unit ideal. So at no point do I need more than twice to derive, but there are points where I need twice. So the maximal order is 2. Agreed? What is the locus where the order is 2? The locus where the order is 2 is a vanishing locus of where doing one derivative was not enough. So I need to have x equals 0, I need to have y equals 0, and that's basically it. So the handle is the locus of order 2, but in fact, this is the correct non-reduced structure of that locus. There's a little bit of extra stuff at the pinch point. The vanishing locus set theoretically is the handle is the z-axis, but there's something at the origin, because this is not just x comma y. Okay, questions about these exercises? Do you know how to go to your room and do the exercises? Here is one example that I want to show you why the Cox construction description of blowups can help you see what happens in the process of resolution of singularities. So this is how you show that when you choose a good blow-up center, then the order of vanishing of an ideal will not increase. So suppose F, so I'm taking a principal ideal generated by one function F, and assume that the order, so this, yeah, Y is now a varying point, what was P before. I'm assuming that along a smooth variety X, the order is precisely A. And I assume that I blow up X. Then I claim that on the exceptional divisor, over the points of X, the order has not increased. And the way I show it is by plugging in the Cox construction and seeing that even before I remove the locus that I want to remove, V of x1 prime through, even before I remove the order did not exist. So I just plug in B. So F1 is a transform, and I claim that F1, the order of F prime is at most A above X. Okay, so let's write F, expand F as the leading term, the part of F that has order A plus higher order terms. And then I plug in the equations for the Cox construction for a usual blowup along the variety X. So the equations are S times Xi prime equals Xi. So each Xi is replaced by X times Xi. So the pullback is replaced by Fa of Sxi prime plus higher order terms. Now this is homogeneous of degree A, so I can pull out S to the A. And then you have the original leading term, but with X prime. And here I have S to the A plus 1 plus higher order terms, which means that F, the proper transform where I cancel off the exceptional part, S to the A, is F is the same leading term now with X prime plus S times higher order terms. So everything here has degree, at least, in fact, here degree A, and S raises the degree even further. But so this has order A because the leading term has just order A. Of course, if we look at the locus where we remove xi prime, the locus where we remove the vanishing locus, all the xi prime, it may drop because there might not be any more points of order A. But if we didn't remove enough, then may not. But the only thing I wanted to show you is that the order does not increase. That good blow up do not mess up too much. And I'm just telling you, this also works for ideals. It also works for weighted blowups, as we'll see in a minute.
For the assumption in red, it means that for every y or for generic y.
So for every point y on x, and I'm blowing up x. X is a smooth subvariety, and I'm blowing up. So this is a well-known argument, but I think it's easier to see what's happening with using the Cox construction. D-star quotient does not change the singularities because I have a smooth action. So in a stack theory, so that's why I work stack theoretically. The stack quotient will not become, if you have a smooth presentation, then the singularities are not worse than what you have above, are exactly the same as what you have above. I don't want to pass to the coarse moduli space. So you're absolutely right. If I go to coarse moduli spaces, then I get something singular. And this is precisely the reason. So, okay, everybody in this room knew for years that weighted blowups are good. I mean, we learned it from Miles Reed. We learned it from Jung-Kai Chen. He has a paper that shows that threefold terminal singularities have to be blown up by weighted blowups. This is the right way to do it. But the reason we didn't do this for resolution of singularities is because we use coarse moduli spaces, which make the ambient space singular. So it's hard to see that something gets better. But with the stack theoretic approach, you see what gets better. It's just a way to see smoothness in a more exotic way. I hope I have not led you astray in this preaching. Okay. Okay. So a little exercise to see what happens to the singularity when you blow up the origin. So we know that if we blow up the origin here, it doesn't get any better. But what we just said, that at least the order did not get worse. Same here and here. If you do it, you'll also notice that if you use usual blowups in this example, things will actually get worse. Not in terms of order, but in terms of the next level of complexity. And that's something we want to avoid, and we avoid it with weighted blowups. In order to do this, we need to use the notion of maximal contact. It's a notion introduced by Giraud and Hironaka. Everything is on the web. You don't need to take pictures. Suppose the order of an ideal at a point is A. We say that an element of the local ring is a maximal contact element at P if it is an element of for the ideal I that we are trying to principalize. If it's an element in the A minus first derivative of I, and the order of the element X itself is 1. So X is regular. It has a non-zero derivative at a point, and it's a member of this A minus first derivative ideal. Why is this important? Well, there are several. So in characteristic 0, maximal contact elements always exist locally at a point. Why is that? we know that the order is A, so we know that if we take the 8th derivative, we get a unit, but if we take the A minus first derivative, we do not get a unit. So the A minus first derivative is not a unit ideal, and the 8th derivative is a unit, which means that you can find an element here whose first derivative is a unit. That's this X that we will choose. That's what a maximal contact element is. So it's a really beautiful. So Hironaka's original paper did not have this notion, but he understood quite soon after that there's a way of really understanding an aspect of what he did in his used paper. And so the exercise is to show that maximal contact elements are not unique. So find two maximal contacts with this idea. Let's do this example. So so remember, the maximal order of this ideal is 2. A maximal contact element is an element here whose first derivative is 1 or is a unit. Can you give me an element in this ideal whose first derivative is a unit? Okay, I mean, people are smiling. Of course, I marked it. I mean, X has first derivative is a unit. So X is a maximal contact because it's X derivative, but also X plus Y squared. I mean, I have the Y squared, I can add that. The X derivative is still a unit. So it's not unique. That is going to be part of the trouble that that Hironaka needed to overcome and we need to overcome. So we did it for the first example, and the exercise is to do it in other situations. And another exercise to show that this notion of being maximal contact is functorial at the smooth morphism. So if you have an element that is maximal contact, its pullback under a smooth morphism is also maximal contact. And that's because of compatibility of derivatives okay, how am I doing with time? I have 20 minutes and I have 7. So maybe I'll postpone the curse of the characteristic for next time, or for if there are questions. There are reasons why. So this is about why things do. So maximal contact is the classical reason why resolution doesn't work in characteristic P. By our current Hironaka methods do not work in characteristic P. But I wanted to say something about it, but it's not urgent. So we know what a maximal contact is, and one purpose of the maximal contact is that you want to use induction on dimension, and you want to reduce principalization of an ideal in an ambient space to principalization of an ideal on a hypersurface. Which hypersurface? The vanishing locus of a maximal contact. Okay, I'll define what it is that I want to restrict to the maximal contact, not the original ideal. So suppose I has maximal order A. The coefficient ideal CIA is defined as follows. You take all the derivative ideals, all the relevant derivative. If you take the 8th derivative ideal, you get a unit. So beyond that, it's not interesting. So take the first, the second, until the A minus first derivative. So that's what I have here. And then you take all possible monomials in these and putting them together, where the weight of the monomial is at least A factorial. So I comes in degree 1, so in degree A, because it's order A. D of I comes in degree A minus 1. D A minus 1 comes in degree 1, because it has a derivative that is a unit. And you take all monomials of weighted degree at least A factorial. So what does this do for you? It combines all possible. So, I mean, if you had so X is a maximal contact for this, but you can't reduce so X is a maximal contact for this ideal, but you don't want to reduce a modulo X because then you get the zero ideal and you lose the information that is hidden here. So this is a way of taking all the coefficients of all the elements and putting them in the right place, so that when you then mod out by X, you get something that will help you. So the exercise to compute the coefficient ideal, it's easy to compute coefficient ideal when the order is 2, because 2 factorial is 2. So it doesn't go very far. It's a bit harder to do it when the order is 5. So this is certainly something that you want to do at home. And the last exercise is the fact that forming the coefficient ideal is functorial under smooth morphisms. That's because derivatives are functorial under smooth morphism because of an earlier exercise.
Can you say again why you want this polynomials of degree 8? Why do you do it?
Because that's the first time where you have something in degree a minus 1, and you want to put them all in the same at the same level. So you'll need to take this to the power a factorial over a. You take this to the power a factorial over a minus 1, etc., and this to the power a factorial. And then the weighted degrees will be the same. And to have things, so that would actually be enough, but to have things sufficiently functorial for something else that will come up, you want to take all monomials. It's just to put things on the correct level together. So a factorial is okay, so you could do the LCM of 1, 2, 3, 4 through a, and that would be enough. So just a few comments. Suppose I have a maximal contact. What are coefficient ideal good for? They come to collect the data of all the coefficients of all the elements of the ideal when expanded in maximal contact. As you'll see in Wodacek lecture, this began with Villamayor and co-authors. You can instead collect everything in a Riesz algebra, which is an equivalent way of putting things together. There are 2 key properties of coefficient ideal. One key property is that improving the coefficient ideal results in improving the original ideal I. And one is a principle of Wodacek, which really, for me, transformed this is the first time that I felt that I can understand how to resolve singularities in Hironaka's original methods, is that maximal contacts X are, so when you form this ideal, all the maximal contacts that you choose are equivalent. There's an isomorphism that takes one to the other. And in particular, if you restrict the coefficient ideal to x1 equals 0, the resulting ideal is independent of the choice of the maximal contact. So there's some fortunate functoriality that comes by virtue of taking the coefficient ideal. So these are just some comments. And now, okay, Evgeny wanted some to know how to choose the invariant, how to choose the center. So hopefully more than just, not just Evgeny. So now I'm telling you how to define the invariants. First, I'll give you examples. So the invariant of this at the origin is 2, 3, 3, and the rationale is that X appears in degree 2, while Y and Z appear in degree 3. So that's an easy case. And you know that life is not always so easy. There's a similar rationale in this example. This is Wodachik's favorite example. And the invariant is 2, 3, 3, 3, because X appears in degree 2. That's the lowest degree. And then the other variables are all appear in degree 3, and there are 3 of them. So that's a 3, 3, 3. Here's a harder example for which I'll draw a picture. X to the 5 plus X cubed Y cubed plus Y to the 8. I claim that the invariant I will choose, I'll show you how to do it, is 5, 15 over 2. So the first part is always the order. The second part is what remains to be explained. So let me draw a picture. And I have dotted page here, which helps. So this is 1, 2, 3, 4, 5. 1, 2, 3. Okay, so the equation I chose was X to the 5 plus X cubed Y cubed plus Y to the 8. Now I have to be very careful. So X to the 5 is represented here. Y cubed, I'm just doing the Newton polygon of Y cubed, X cubed is here, and Y to the 8th, 1, 2, 3, 4, 5, 6, 7, 8 is here. Okay, so maybe I'll change it. I'll change it to Y to the 100. So I can draw it a bit easier. Okay, so what's a Newton polygon? It looks like this. So the first part of the invariant is the order is the first. So I'll start looking. What is the first time I hit the Newton polygon? First time I hit the Newton polygon is at 5. So maybe I want to. Now, what I do now is I try to project from this point. Okay. It's supposed to hit at 7.5. I don't think I drew it perfectly. So I claim that it hits at 7.5, and that's the other side of the. If instead I had X to the 5 plus X cubed Y cubed plus Y to the 7, then a Y7 would lie below, and that would be X to the 5 Y to the 7. Okay. So that was just examples to get an idea, a rough idea, but let me now tell you how to do it. This didn't teach you how to do it. Before that, I'll tell you how the centers are put together. So the center of this is going to be X squared, Y cubed, Z cubed, which is precisely what you get by taking the relevant variables and putting them in these powers. The center for X for this is X squared, Y1 cubed, Y2 cubed, Y3 cubed. Here I have X to the 5th, Y to the 15 over 2. So you notice that the powers can be fractional. And if I had a 7 here, then, okay. Now I need to tell you how to do it really. Let me tell you how to define the invariant and the centers. And the definition is inductive. So assume that the order at a point P is A1 with X1 a maximal contact element. I told you how to compute the coefficient ideal, and I gave you, so I2 is the coefficient ideal, or A1, restricted to x1 equals 0. And assume that the invariant of this, this restricted coefficient ideal has already been defined. So I'm doing something inductive. Assume that the invariant is B2 through BK. And assume that I already defined the corresponding center for this coefficient ideal, restricted coefficient ideal, x2 to the B2 through xk to the BK. These x's are going to be regular parameters at the point. Now, coefficient ideal was obtained by putting high powers of various ideals. I need to scale back so that everything is back to the level A1. So I divide the BI by A1 minus 1 factorial. That guarantees that I take A1 factorial and divide it by A1 minus 1 factorial, I get A1. Okay. The invariant will be obtained by taking these AI and adding them. So this A1, A2, AK. So appending these terms, rescaled like that to A1. And the center is obtained by appending this rescaled to have the AI here, appending it after x1 to the A1. So let's see. So the exercise says verify the invariance and center in our examples. So I think I have time to do this in one example. So I did the example x squared plus y squared z equals 0. I said so x is a maximal contact. Order is 2. So I need to have x squared and something. What is the something? The coefficient ideal of C of I2 restricted to x equals 0. It turns out to be just this term. Okay. We have two maximal contacts here, y in degree 3 and z in degree 3. So y order is 3. And because they appear in the same order at the same degree, I might as well take them both at the same time. They both appear in order 3, so the center for I2, this is I2. Center of I2 is y cubed, z cubed. And I just append this here. So I get x squared, y cubed, z cubed. And you have exercises to verify this in all those cases. The invariants and centers are functorial. So this is a theorem that we proved. If I have a smooth morphism, then the invariant of the pullback ideal at the point above is the invariant of the ideal at the point below. If I have a smooth morphism, then the point above maps to a point below, that the center above is a pullback of the center below. And we'll see, well, next time we'll see that this implies both gluing and equivariance of, so we can glue things together. And we can show that the result is in equivariant under group actions. So functoriality is a very good property. And finally, I'll state the main result, which only works in characteristic 0. I guess, okay, so now I told you that I'm doing it in characteristic 0. If I take, so y prime, there's one thing I need to tell you, and I'll tell you next time. Y prime is the blow up along the Okay, basically the center of Y. And then the invariant of the coefficient ideal. So C prime is a transformed coefficient ideal. The invariant of the transformed coefficient ideal drops, strictly drops. And with Collat's principle, this implies that the invariant of the original, of the transform of the original ideal drops. So this is the main result. If I take the blow up at the center that I just told you how to take, I will repeat that next time. And I take the transformed ideal, the invariant of the ideal drops. What does that mean? If I need to convince you that the invariant lies in a well-ordered set. Therefore, this can happen only finitely many times. And when I'm done, the thing is resolved. Maybe even more convincing is if you sit down and do the examples by hand and see, in fact, that the invariants drop and things get truly better at each step. I think this is enough for today. I mean, this is about halfway through, and we have exercise and examples to do next time, and proofs to do next time.
Okay, so thank you very much. So do you have any questions?
I don't know what this silence means.
Can I ask just so at the end, when this invariant stops dropping, why is our ideal locally principal then? So something obvious, but like
So at the end, the transform ideal. So the only way you can it can stop is when the transform ideal is one, is a unit ideal. So each time you remove the exceptional. So you remove the exceptional, you have the non-exceptional part. So at the end, the only way it will stop is that the non-exceptional part is the unit ideal. So the order of vanishing is 0, and there's nothing to do.
Thank you.
So you have a functorial resolution by some smooth Denis-Manifold stack.
Right.
Yeah, and from smooth Denis-Manifold stack to smooth varieties. So
that's what I called destackification. So at the end, so hopefully, I mean, there are many things to say. You know, this is resolution of singularities for everyone, but what I can prove is, I mean, I have only 1 hour and a half next time, so I'll prove some things. But with, you know, you can, the paper is only 20-something pages, so you can actually read the whole paper in a reasonable amount of time. So, but the final step is, if once you have a smooth Denis-Manifold stack, there's a well-established procedure to take it, blow it up, and do some root construction and blow it up, so that the coarse moduli space of the result is smooth. So you have a smooth stack whose coarse moduli space is still smooth. That's very special.
and this is also a functorial.
And this has a different functoriality property, but yes, it's also functorial. It's functorial for smooth morphisms, yes.
Oh, thank you.
Maybe even easier. So you got a smooth stack which has a billion stabilizers. Its coarse moduli space is a variety with a billion stabilizers. Now, since the 90s, people have devised ways to resolve singularities of varieties with a billion stabilizers, and it's much, much easier than Hironaka. Now, of course, to do it functorially, this is, yeah. So there's something called Berg's destackification, which is totally functorial and it can do it for you, but there's various ways to do this. I'll tell you, I'll just give you one or two examples to convince you that it can be done.
So are there more questions?
Again? we use, so the invariants are in fact, well, they're not exactly in Hironaka, but they are in both Villamayor and Birational in a slightly different form. So because they have to do something else, they have to make their invariants more complicated. But in essence, you can find the invariant in their work. So the invariants are there. In a way, the center is there. There's a thesis of Boris Yusin where the data of writing out the center is basically equivalent to what we wrote. But blowing up that center in a stack theoretic sense, that's different. I should say there's a parallel work by McQuillan who proved the same thing. So you'll also find a paper by McQuillan. It's I mean, the methods of proof are somewhat different, but McQuillan, yeah, works also with weighted blowup. So we put it on the archive the same day. There's a story about it, but maybe Evgeny knows it. Oh, it's Nikes. Your collaborator Nikes knows the story.
More questions? So if not, then let's thank Professor Abramovich again.